right? You all know this. He saw all round. He didn't see puckered, slightly puckered, or anything like that. He didn't see any wrinkles. They were all every bit as round as the rounds in the parental generation. That was an extremely important point because, of course, a competing theory of inheritance was blending inheritance, where the offspring would be intermediate. And the truth is, almost every experiment that you do, when you take plants and you cross them, or animals and you cross them, despite your biology textbook, shows blending inheritance. A tall plant and a short plant, you breed them almost always as a middle plant. But not for the peas. The peas were a beautiful system. And Mendel was very lucky to have chosen them because the truth is, there was only one gene difference that was controlling these traits. If there had been 10 genes controlling this, you'd get some blending, blah, blah, blah. But Mendel got a situation with really clean experimental data. The round was every bit as round. And so that said, no blending. Now, what did he do? Next, what Mendel does is he crosses these round peas to themselves. He selfs them. So we're going to self the peas. The peas can be selfed. They have both male and female reproductive parts. And when he selfs them, they self-pollinate. And what do they produce? Peas, right? That's good. And they produce peas. And what does he notice? He notices that now they're not all round. Some of them are wrinkled. And the wrinkles are every bit as wrinkled as the wrinkles were in the parental generation F0. And the rounds are every bit as round. So suddenly, wrinkled had gone away. And what had happened? Sorry, wrinkled had gone away in this generation, and now it had reappeared. The trait reappears. It's quantum. It's discrete. It's not blended out in any way. It's not blended. It's not imperfect. It's the same wrinkle that was there before. That's a big qualitative observation. This whole blending notion can't be right, at least for this experiment. Discreteness rules. So, that was his experiment. Mendel could have written it up and said, wow, the traits don't blend. They're discrete. But Mendel, being an MIT kind of monk, went further. What did he do? Sorry? He repeated it, and it still showed some rounds and wrinkles and all that. But he was a very quantitative MIT monk. He counted them, which seems obvious, but ain't so obvious. He counted them. And what did he find? Fixed proportions? A ratio. 1 to 3 or 3 to 1 or something like that? No, he counted. He counted, and what he found was rounds, 5,474, wrinkles, 1,850. Ratio, not 3 to 1 at all. 2.96 to 1. No, but you see, you say, because your books all tell you 3 to 1, that it's obvious if you do that. You say, that must be 3 to 1. That must be 3 to 1. It's 2.96 to 1. And if you do it again, you might get 2.87 to 1. And it actually takes quite an imagination to say, it's trying to be 3. Just think about it. You come to this experiment, you say, it's trying to be 3. That's a separate leap and an important leap. He counted, and he got numbers. 2.96 to 1, and he got other numbers. He then, as you've done so quickly, made a hypothesis. That hypothesis was that, in fact, this was trying to be 3 to 1, that it, quote, wanted to be 3 to 1. It was near 3 to 1, and that really, the reason it was trying to be 3 to 1 was because, well, there was a pretty nice explanation here. His cool explanation was the round plants and the wrinkled plants, well, he made up a model. These guys had 2 particles of inheritance, big R, little r. When you cross them together, these guys were big R, little r. And when you self them, if you randomly chose 1 particle from the sperm and 1 particle from the egg, ovule, you would have big R, big R, big R, little r, big R, and little r, all as possibilities. And that these guys, big R, they would be round. Why would they be round? Well, because that's what the parental generation here was. The little r, they would be wrinkled, because that's the parental generation there. And these guys that have 1 of each, what would they be? Round, because we saw that in the F1 generation, 1 of each makes it round. So we had a model, a hypothesis, a model. Pretty cool. You can come up with this model by saying a contribution from the male, a contribution from the female. This is the male gametes, the female gametes. You get this nice little thing sometimes referred to as a Punnett square, although he didn't use Punnett squares, and Punnett wasn't born yet. Now what do? Mendel went out and got experimental material. He did controls. He did an experiment. He counted. He then made this creative leap to say, I see something kind of cool going on. I think integers are what's going on. And made up a model. What does a scientist do with that? Sorry? Oh, come on. In this modern world, if you got a result this cool, what would you be doing? Sorry? Publish it, right? You're going to get out there quickly and publish it. Mendel whips off an email to Nature in London saying, or the 1865 emails. Actually, it wasn't Nature. It gets published in the Proceedings of the Royal Society of Brno, but forgive me, I'll use Nature, okay? So he whips off an email to Nature, which is what we do today, telling the editor, we have this really cool result. I think it'll be of broad interest to the readers of Nature. We're going to try to send you a paper next week, et cetera, et cetera. Are you interested? They write back, oh yeah, we'd love to see your paper, Gregor. And Mendel whips together a paper. What happens when Mendel whips together this paper and goes off to London, to Nature, the offices of Nature? What does Nature do with it? They just set it in type and say, here it is? What's the scientific process? Peer review, right? Before you go print this thing, you got to send it out to some other scientists, as anonymous reviewers, and say, we've received this paper, this correspondence from, Brother Mendel in Moravia. Would you review it for the journal Nature and tell us your candid opinion? And they write it up and they send it back to Nature, and Nature makes a decision whether to publish the paper. So you're the reviewers. Should we publish Mendel's paper? Who says yes? Who says no? Why no? Needs more examples. So you're right, one lousy trait. Mendel actually had 7 traits in the paper. It turns out I didn't tell you them all. Green and yellow and tall and short, and they're all in the paper. He actually has 7 separate examples that show the same thing. Should we publish it? Why not? It's just peas? Oh boy, you're churlish there. I mean, come on. It's peas. It's, people eat a lot of peas. It's a result. It'll get others in the scientific community interested. Who are the peer reviewers? I've assigned you as peer reviewers. I'm asking you, should we publish this thing? We got 7 traits. We're going to publish it. It's pretty cool. Nobody's ever reported this 3-to-1 ratio on this model. Well, you are now. You'd publish it. Okay, he'd publish it. Because nobody's reported this. It's pretty cool. The model perfectly fits the data. Yes? It's got to make predictions. But the model fits the data. Are you saying that we made up the model after we saw the data? And that it's not a surprise that the model fits the data? Yeah, that's right, isn't it? That's a real problem. If you make up models after they fit the data, they tend to fit the data. Well, they do. That's a real problem. So the reviewers write back to Mendel and say, Mendel, this isn't actually how it happened, you understand? But anyway, they write back to Mendel, they write back to the journal Nature, and they anonymously say, we would like to see some predictions of this model to see if this is really true. And Nature writes back to Mendel, and the email says, could you show us some predictions from this? So help Mendel out. What predictions can we make? What surprising predictions could you make for Mendel's experiment? Well, this experiment, round by wrinkled, gives rounds, gives some rounds and some wrinkles, which we think are big R, big R, big R, little r, little r, big R, little r, little r. But this is big R, big R. How could we prove something's going on in this generation? Self them. If we pick out a round and self it, what's going to happen? Sorry? Depends. So how do I know which round to pick? They all look the same. Try all of them. If I try all of them, what am I going to see? Produce round. About what fraction of them will only produce round? 1/3. And what fraction will produce rounds and wrinkles? 2/3. We have a prediction. Thank you. The prediction is test the rounds. And although we don't know which are which, 1/3 of them will give rise to only rounds, whereas 2/3 of them will give rise to our 3-to-1 ratio. That is a non-obvious prediction. If this model weren't right, it's very surprising that you would have nailed that prediction. Nice. What other predictions can you make? What other crosses could you set up to test it? The wrinkles by themselves will only give wrinkles, and that's true. Bingo, so we're doing well. What else? Wrinkles with rounds. So I could take these 3 rounds here, and I could cross them to wrinkles. What'll happen here? If this was round over wrinkled, it's going to give rise to what? All rounds. But if this is round wrinkled, what will it give rise to? 50-50. Half a half. Now we're cooking. There are all these predictions that start dropping out because your model tells you things you haven't yet seen.